Similar to a vertical well, the hole is drilled to just under the deepest fresh water near the surface. The drill pipe and bit are then removed.
What goes in next?
Surface casing is inserted into the drilled hole to isolate the fresh water zone and also serves as a foundation for the blowout preventer, a safety device that connects the rig to the wellbore. Then, cement is pumped down the casing and out through the opening of the shoe at the bottom of the casing. It is then forced up between the casing and the hole, sealing off the wellbore from the fresh water.
Steel,
the cementing process prevents
rock.
any contamination of the freshwater aquifers. The pipe and bit are lowered back down the hole to drill through the plug and cement, and continue the vertical section of the well to approximately 500 feet above the planned horizontal leg. This depth is called the kickoff point, where the curve will begin so the horizontal section can be drilled. Up to this point, the process is the same as drilling a vertical well. Again, the pipe and bit are pulled out of the hole, and a downhole drilling motor with measurement while drilling instruments is lowered back into the hole to begin the angle building process, same as drilling a vertical well. Again, the pipe and bit are pulled out of the hole, and a downhole drilling motor with measurement while drilling instruments is lowered back into the hole to begin the angle building process. The distance to make the curve from the kickoff point to where the wellbore becomes horizontal is just under 1/4 mile. Once the curve is completed, drilling begins on the well's horizontal section, called the lateral. The pipe used to drill the well measures 30 feet in length and weighs approximately 495 pounds each. It takes over 350 pieces of pipe weighing nearly 87 tons to drill a 10,500-foot well. At various stages of drilling, the pipe is taken out of the hole for tool and bit changes and put back in. This process is called tripping pipe. When the targeted distance is reached, the drill...
Okay, one of the questions was how far can they drill horizontally? The answer is almost as far as they want. Certainly thousands of feet. I mean, there are wells, I doubt whether wells like this in Marcellus will occur, but there have been wells other places in the earth where they've gone horizontally for more than 1 mile. Okay, so the limitation there is the technology and the economics. The farther out they go, the more energy and cost they have to put into drilling the well. And at some point, there's an intersection between what they think they're going to get out in terms of profit from gas and the amount of money they put in, and that's where they stop.
Pipe and bit are removed from the wellbore one last time. Production casing is now inserted into the full length of the wellbore. Cement is again pumped down the casing and out through the hole in the casing shoe, forcing the cement up between the casing and the wall of the hole, filling the open space known as the annulus. Casing the well is a very important process because it permanently secures the wellbore and it prevents hydrocarbons and other fluids from seeping out into the formation as they are brought to the surface. At this point, the drilling rig is no longer needed. A temporary wellhead is installed and the location is prepared for the service crew who will perf, frack, and prepare the well for production. The first of these steps is to perf, or perforate the casing. A perforating gun is lowered by wire line into the casing to the targeted section of the horizontal leg. An electrical current is sent down the wire line to the perf gun and sets off a charge that shoots small holes through the casing and cement, and out.
So now I'm going to give you something that I've never given any other audience I've talked to. And you will not have seen what I'm going to show you in any other article, journal, newspaper, or TV ad. I'm going to show you, that's a cartoon of the perforating process. It's a cartoon that says, here's steel casing and it's surrounded by concrete. I'm going to show you what it really looks like. In the late 1980s, I had a project with Schlumberger, and we did full-scale physical tests of this process on the surface. We acquired large blocks roughly 10 feet by 10, a cube of rock, 10 feet on a side. Drilled into it, inserted a casing, cemented the casing, put down a drill string with perforating charges on it, perforated it, hydraulically fractured it, and then broke it open to see what it looked like. Cool. They pay me to do this. Can you imagine getting paid to break things? This is a block of rock. We had to saw it, to break it open eventually. This is where the casing was. I'm going to show you details here. This is where the casing was. There was cement surrounding the casing, and there were perforations. And this red area, we injected red dye into the fracturing fluid. So we could see the shape and the number and the orientation and the size of the hydraulic fractures. That's cool. I mean, that's physical verification of somebody's computer model. We predicted by computer what would happen. And boy, were we wrong. We weren't even close. But, you know, facts don't lie. So let me back up a step here. You're the first to see this. All right. Here's a closer view. Here is a perforation. That's a hole that's punched through the steel and the cement. This is cement. This is steel. Here's another hole that came out of the cement, went through the steel, went through the steel, went through the cement, and here's the hole actually coming out in the rock. And you can see that when we pump fluid into that perforation, the fracture started here and propagated. And this is actually the edge of a hydraulic fracture. It's a very small one. The hydraulic fractures that are being put into the Marcellus are thousands of feet. But they all start this way. They have to start at these little holes, and all the gas that comes out has to go back through those little holes. Isn't that cool?
For distance into the shale formation. The perf gun is then pulled out of the hole. Next, because the shale is tight or compressed, the well will have to be fracked. Known as hydraulic fracturing, this is a process where water, sand, and lubricants are pumped into the wellbore and down the casing under extremely high pressure.
Water, sand, lubricants,
as the
and
mixture
others.
is forced out through the perforations and into the surrounding rock,
That
the
doesn't look
pressure
like the
causes
fractures
the
I saw.
shale
That's
to
a
fracture.
cartoon.
This creates a fairway connecting the reservoir to the well and allows the released gas to flow to the wellbore. Next, a temporary plug is placed at the heel or left side of the first stage frac. The plug closes off or isolates the perforated and fracked section of the wellbore so that the second stage section of the horizontal leg can be perforated and fracked.
So hydraulic fracturing of a well can occur many times, not just once. That much water for each of 10,000 wells. And on any one day, you're not going to drill 10,000 wells. There might be 4 or 5 wells being drilled on any one day, where you're going to get 50 million gallons of water. Not out of a small stream that's running outside of town. You've got to go to a big source, a lake or a big river. Can't go to the Delaware. Can't touch the Delaware. Susquehanna says, go for it. Okay, so they're going to be drawing water out of the Susquehanna, or they're going to be trying to draw water out of large bodies of water, aka lakes. Once that thick water goes down there, goes into the fractures, carries the sand into the fractures, you don't want that sticky, gooey stuff in the fractures anymore. That's going to mess up the gas flow. So now you have to pump another fluid in that breaks down the thickener. That's called a breaker. Getting the idea here? So the right chemicals in the right order, in the right percentage, and you got yourself a good hydraulic fracturing fluid. Now there's another problem. These organic chemicals, the gelling agents and the breakers, bacteria love to eat them. So if you're storing them at any period of time, or when they're down the hole, you don't want the bacteria to start eating them. That upsets the chemistry. So you pump down a biocide, something that kills bacteria. It's okay when it's down there. You don't want it in your trout pond. Fluid loss additives. You don't want the fluid that you're pumping down there to leach into the rock. That's called fluid leak-off. Why? Because it clogs the pores and the gas can't get out. So that's another chemical that's added. Anti-corrosives. You saw the amount of steel that goes down there? And all that fancy motor that turns the drill bit, and all the fancy instrumentation that goes down there. You don't want it to rust. Okay? And down there is a lot of salt water. So you've got to have anti-corrosives. And you don't want to use any more pump power than necessary to pump large volumes of fluid at very high pressures. We're talking thousands of horsepower to do this. So you can add friction reducers so that the fluid flowing through the pipe doesn't experience as much friction and back pressure. So those are the major categories. There are other minor categories of agents added to the fracturing fluid. Okay. Taken individually, one could argue pro and con any one of these things. I would ask anybody in this room, would you want to drink a cocktail of all of them together? No. Okay. So it's best that they're left down there, or if they have to come back up, appropriate measures are taken to reduce to an acceptable level of risk harm that they can do to people that don't want them.